Hi, my name is Sean Morris. I'm here today to share my research on the declarative integration of CAD software with multiphysics simulation via constraint hypergraphs. This research is done by myself as well as my advisors here at the Department of Mechanical Engineering at Clemson University. This work will be presented at the ASME IDETC-CIE conference in Anaheim, California in 2025. I want to motivate this work by saying that everything in the world is a system. The whole world is composed of things that are systems, and it's our work as scientists and engineers to characterize these systems. In fact, the goal of an agent that's using these systems, interacting with them, is to observe things about the system, what information we can extract about the system. We call that information its state. It might be, I might want to know when the batteries in my toothbrush are going to die, or how much more gas I have in my tank. I want to know what time the sun is going to come up, where the weather is going to be. Whatever it is that I'm doing, I need to know information about the systems I'm interacting in order to do that thing. We often form complex models in order to represent these systems. These models are usually represented across a variety of different formalisms in software, CAD, programmatic things, databases. They all help us to capture, again, this information that we're trying to understand. This kind of motivates one of my more favorite perspectives of systems, which is that a system is a collection of variables, which Ross Ashby said in his Introduction to Cybernetics. So for instance, here I have distributed several different models of a IC engine crankshaft, something that's turning around and turning the cams or pistons in an engine. So I might have geometric information that is in Onshape in CAD. I might have timing information that I keep in some kind of synchronizer. I might have structural information in ANSYS or in a database. And then I might have my kinematic variables over here. If I zoom into here, let me show you an actual model and we can actually see what this means. So here I have a kinematic description of a slider crank mechanism. And I've identified 4 different variables in it. That's all that this system is really composed of. That's the rotation angle for this slider arm, the length of the crank, the length of this drive shaft, and of course the vertical position of that drive shaft. There's could be more information to find here, but in this system description, I've only said there's 4 things. I've only identified 4 variables that we can know. And those are what we're going to be working with as a system. If I can just tell you the values of all of those variables, then I fully characterize the system. You know everything there is to know about that system. But if I can't observe some of those variables, what I have to do is provide a model that helps you to see the relationships between them. We often do this with equations. So here's a very nice set of equations that helps us to see um, a model as we're identifying the behavior between all these different variables. When we write behavioral models, we do so in the way of functions that says that the behavior of this variable, or the value of it, is in some way related to the values of the other variables in the system. So here's a function that if I know the vertical displacement and the lengths of the crank and the drive shafts, I can plug into this function, and I will pop out the crank angle. And similarly, if I know those informations on theta, I can do and find the vertical displacement of the drive shaft, y. In each one of these cases, I'm taking a function, passing variables into it, and getting out some other variable. That is the definition of a function. And I'm using that to understand the behavior of my system. Once I have the model, all these relationships, I can actually do that to do simulation. Simulation is when I actually put numbers into these variables and use the functions to get other numbers out. Those are artificial numbers that allow us to actually see what this model is doing at a specific time. So if I give you a number for this length and I give you a speed, I can actually get out the vertical displacement. And if I do that enough times, I can plot it and we can get these kind of cute animations that shows the motion of this slider crank system. And we do this a lot, and there's a couple different ways that I want to talk about simulation, because in our work of engineering, we're constantly having to simulate our systems. All the information we're getting out, we either are observing it or we're simulating it in some way. And so the way that we do simulation actually has quite a bit of impact on how effectively we can do our engineering work. So the most traditional way of doing simulation is called imperative simulation. And in this, we are taking a set of inputs and transforming them into a single output. And we do that with some kind of explicit sequence. This is a model in Simulink. You can see it has a bunch of variables over here. We would put values into them. You can see the values that are being inserted right here on the left. Those values get transformed. Here's a function here. The output gets passed to this function, then to this function, and then finally to our overall output over here. This is actually a model for a pendulum. You can see as we pass these values in, there's some specific process that converts the values on the left to the output on the right, and that is our simulation. And we can do this similarly back with the crankshaft. I can see here's two different models for calculating two different variables in our system. These are based off of all the model behavioral relationships that I gave earlier with those algebraic equations. So here, again, with MATLAB, a very kind of similar process. We have all of our inputs here at the top, and we plug and chug down the way through our program, and at the end of our program, we get all the values out. So this one takes omega in and transforms it into y, and this one over here is a different simulation, different program that takes y and converts it to theta. You can see that there's a lot of similarities between these, but they are different programs. You have to write them out explicitly. They are different in the different programs that you arrange. And this is one of the things with imperative programming that's important to recognize, that you have to write a unique sequence for every single input-output pairing in your system. And if you're doing imperative programming, there's no way to say this chunk over here is connected to this chunk over here. You have to kind of rewrite it every single time. There's ways, of course, to get around this, but this is the kind of outcome of imperative traditional programming, that we are tending to write a lot of simulation programs. And let me kind of show you this kind of graphically what these simulations look like. So we can arrange these as trees. Here with trees, all of the leaves of the simulations are leaves. So you can see the leaves down here in black with a bolded edge, and those get converted by our functions. You can see these functions here into our outputs, which here are blue. Here's a tree going to T. Here's another tree coming from these inputs to Y. Here's another tree. Here's that same tree going to T. And here's the tree that I just showed, the MATLAB program, going to theta. So this is the graphical depiction of the previous slide with two different simulations. You can see again a lot of crossover, a lot of the same variables being used, a lot of the same functions we talked about before, a lot of the same inputs over here. But these trees have to be explicitly stated when we're doing imperative simulation. There's a MATLAB program for each simulation we want to run on the same model. This complexity of writing all these different simulations kind of scales very, very quickly and get out of hand and become untenable very quickly. So for instance, the maximum number of input-output pairings in a system of n state variables is actually given by this formula over here, which is the sum of n minus I times the combination n choose I for all values from I equals 1 to n minus 1. And that is a exponential function. It's actually a little bit worse. It's order of magnitude worse than basic exponential functions. You can see if you're on this logarithmic plot, to the point where with 5 variables, there's 75 maximum simulations you might have to run, or all the way up to 25 different state variables. We're already on to 400 million possible simulations that you might have to write. And again, these are all the possible input-output pairings. In practice, this looks a little bit better, but again, the scale is on the same kind of magnitude. We scale quickly, and it quickly becomes impossible to fully simulate a system. You can have one model with all these relationships, but you just can't write every single way to get from one variable to another. So the way the other side of imperative simulation is declarative simulation. Declarative simulation is still working with the same functions and variables, but we're going to express them in a way that allows us to not have to explicitly write out every single sequence. What we need for declarative simulation is some kind of mechanism for building the simulation sequences as we need them, so we don't have to write out every single one every single time. And the way we're doing this is with a constraint hypergraph. This is a modeling formalism that we introduced earlier this year in the Journal of Computing, Information Science, and Engineering. A constraint hypergraph represents a system as a set of variables. Those are the nodes. They're related by a set of edges. Those are the arrows here. We've actually labeled our edges as black boxes so you can kind of see the inputs and outputs. These black boxes or edges are just functions, and they relate each of the variables. So the same functions we've been seeing, the same ones that were written as equations on the earlier slides, are here written. You can see all the relationships. So for instance, this one is a function for calculating y, as it takes as inputs the length of the slider shaft, the length of the crankshaft, and theta. And you pass those into, and you're going to get y. And every single function that we have in our model is represented here in the system. This is a complete and total representation of a system. Every single system behavior that you could represent on a system can be shown here. That is nice in and of itself. But perhaps more importantly, we can do simulation on this declaratively. And that's because every single one of those explicit simulation pairings, input to output, can be described as now a path in the hypergraph. Because we have paths, we actually get a minimally representative set of all those different simulations. So normally, if you had 7 state pairings, or sorry, 7 state variables, you could have as many as 440 actually, different pairings between those inputs and outputs. But here we can just show those on the graph. So the 2 trees we had before are here shown. I've taken this graph and duplicated it. This is one graph, But here's one simulation on it, taking from the nodes with the bolded black border all the way to the blue nodes. And here's another simulation on the other side. Same graph, but a different path gives us a different simulation. We haven't had to change anything. We haven't had to rewire or rewrite one model, and we get all the simulations out of it immediately, as long as we can do autonomous pathfinding. To do that pathfinding, we've written a software called Constraint HG, which takes in your models, builds this large constraint hypergraph, and then you pass it your inputs, and it constructs the output and finds a path from the inputs to the output. So they can find that path and construct that simulation for you. Again, this means that you might have, hundreds of millions or more different simulation paths, but the solver can find those autonomously without you having to write out a new simulation for every single pairing. So let me describe the actual process of constructing these constraint hypergraphs. So first off, we start off by identifying the system facts. These are the things that you can know about the system. We might have 4 here, A, B, and C, and D. These represent parameters, application variables. They might represent API tokens, but there are things that we can know about the system that we're modeling. The second thing we need to do is form the relationships between these variables. So we might say that A goes to B, and B and C both go to D, and those are what we know about the relationships. We take that hypergraph that we formed and we pass it to the solver, constraint HG in this case, which is going to parse and identify all those relationships. And then all we have to do is request a simulation. This is the declarative part. We declare a simulation, and the solver solves it based on the information we've given it. So I might say I have inputs of A and C. I know A equals 3, C equals 5. The solver will go through and take those inputs and find a path that connects them to the thing I want to know, which in this case is D, and turn 3 and 5 into 2. And that's a full simulation. Now, the idea is we can now do this with more than just algebra. Here, the negation and summing functions are being done by you in your head, or maybe by a Python or MATLAB script. But we can do more complex stuff by using different softwares. And there's often times that we want to use different softwares to do different simulations. For instance, I might want to do kinematic analysis in MATLAB, and I might want to find mass properties in CAD. This is specifically important for CAD, right? We love doing stuff in CAD because CAD can quickly calculate moments of inertia and volumes and weights and material properties. We like that because it's quick and does all the linear algebra for us. And so we want to do a lot of our simulation in CAD. But how do we connect that back with the kinematic analysis we're doing in MATLAB and the geometric specifications we have in some kind of program script or in PDM software? How do we connect those together? Well, the secret is to put them all into a constraint hypergraph. If you do it imperatively without that, then you end up writing one simulation for every single combination, every single relationship that you have between the geometry and MATLAB and Onshape. But if you do a constraint hypergraph, you get one big model, and you can do all the simulations on that model afterwards. You don't have to write out every single path, every single input-output pairing. So let me show you an example. This is a subset of a larger hypergraph that we can use. This takes in inputs over here. These are physical parameters, and it's going to go through and actually construct a CAD model using the API for Onshape. We're using Onshape because this API is pretty widely available. You can go and replicate this right now, as long as you create an account with Onshape. So we take this, we convert this, you can see all the blue highlighted features. Those are the CAD functionalities. So we're creating features, we have the IDs, the operation types, the names. These are the parameters we're using to actually do the CAD. And we take that and we call the API of Onshape specifically. So that's we call Onshape specifically to create these different functionalities. In order to do that, we have to access the API, but you can see that we actually can do that here. We can put the different tokens and IDs that we need in order to access the API as variables in our hypergraph. And as we pass those in, I'll color those in purple. And that gives us this kind of long process that takes in a couple of dimensions over here and spits out a moment of inertia. I could take that moment of inertia and pass it back to MATLAB or vice versa. Here, most of the functionalities are done in Onshape, but I could also quickly add on functionalities in MATLAB or in ANSYS or some other software and allow me to quickly create this declarative interface that gives me all the information and relationships between my total system. Holistic. You might ask, that's nice. It sounds nice to not have to do too much programming, too much more writing, but again, what is the purpose of this declarative simulation? Well, I have a kind of a dumbed down version that allows us to see some of the impact of this. So here's this idea that we have 4 concentric cylinders, and we want to put them all into a single line. In an imperative model, the order matters. So you might put A first, and then write B, C, and D afterwards. But if you remove A or don't put an A, you can't do B, C, and D because they are all dependent upon A. And we know that from a CAD. You have a hierarchy tree, right? You start off with your base, you make your other things on top of the base. If you remove the base, everything else disappears. But with declarative modeling, that's not the case. If I get rid of A, everything else still exists because they know the relationships between all the other variables. There's not just one relationship, all the relationships are captured in the model. So I can do things out of order. I can put C in first and B and D and A. As long as I have one cylinder, I know that the position of all the other ones are set because they're all concentric to each other. This really captures the behavior of the system rather than just my modeling constraints where I was having the order of my modeling preferences. So what are we going to do with this? Well, the idea is that if you can capture all these behaviors across all these softwares and all these different formalisms and really drill down to the behavior of the system, then what you might have is some kind of foundation for model-based engineering. Really, in here, we're kind of only restricted by the quickness that we can code, right? How quickly we can wrap the APIs of these different softwares to access their functionalities. If you can do that for different software packages, then you can write those functionalities into a single constraint hypergraph, and you're left with not a lot of different models that you're hardwiring together imperatively, but rather one system model with one set of variables for everything that calls out and captures information cohesively, giving you a unified structure. And whether your information's in PDM or in Onshape or in ANSYS or in ROS, wherever it is, you can capture it and bring it together and see how one part of your system on the analysis side or the cyber-physical impacts the structural and the database and the or organizational. All those interactions are captured in one single model. We're very excited about the implications of this, and we are working on lots of exciting projects with this. If you feel like this might be useful in your own work, please get in contact with us. You can find more information about this system, about our software by going to our documentation where we have videos and other resources. This QR code will go there. Otherwise, you can Google Constraint HG. We'd love to get in touch and work with you more. And thank you for listening to this presentation.